Hello, everybody. This is Brendan, and I'm here with Daniel. And we are, I'm going to let each of us introduce each other a little bit, but we've been really into the UAP subject for a long time, watching the skies and trying to figure out what is going on up there in terms of physics. And a lot of these observables, the five observables, as we call them, and I'm going to have to be reminded on the very specifics, but one of them is like complete silence. One of them insane speed.
So there's low observability, signature management, instantaneous acceleration, positive lift, and hypersonic velocities.
Yeah, and these are also accompanied by crazy maneuvers, such as like sudden stopping and then sudden going,
which would be the instantaneous acceleration.
Yeah. And deceleration, which I find especially interesting. Like, if you did that in a car, you'd be jelly on the windshield pretty quickly, or worse, right? And just the speeds that these things are traveling, that's a ton of energy to just change direction.
For sure, the energy part. So let me ask you this: what's your what's your level like technical background in physics? Just so I know to like what language.
It's not. I'm actually, I'm a physicist, script kiddie. And I guess you could call me as, I'm an amateur for sure. And,
me too.
And no, you're much farther into it than I am. Trust me.
I'm not a publishing physicist and I don't have any degrees. So just take everything
you can write the math, the code, you can write it down. I've been watching like PBS Nova, these kinds of things, history of the universe, lots of things that more recently, but kind of had these sorts of things osmosing in my brain for years and years and years and years. Science Channel, Discovery Channel, every time these subjects come up. So I'm familiar with figures with like Brian Greene, Sean Carroll, listening to Leonard Susskind go off, listening to Jack Sarfati go off more recently, Sal Pais go off more recently. I've listened all the way through all of Kurt Mungel's UFO and exotic research podcast probably 3 times, and I still don't get 75% of it. But it's deeply fascinating to me, and I want to grasp the mathematical concepts, and so I'm really glad to have help with that.
So, like, I'm not even that good at them. I'm not good at the math. I'm good at the physics. Again, so don't believe anything I say.
Mm-hmm.
Go out and research this stuff for yourself, because it's all out there. If I can learn it, you guys can all learn it. And I'm going to try to send you guys documents to everything I'm referencing throughout, so you can link and put stuff in the description and stuff. So let me ask you this: so as you understand it, like where is your current understanding and how you think these craft are moving?
Okay, so my understanding is that they are somehow creating a kind of space-time envelope that is based on a metamaterial structure that's got a superconducting hole that's connecting to another metamaterial structure that's on the inside. And this is just what I've come up with in my mind in terms of the structure, and that those metamaterials are configured in such a way with such atomic layering, precise isotopic ratio, atomic layering that's deposited there, I think by some sort of nanomolecular process, basically a chemical 3D printer sort of thing. And that's just the physical end. But what those are doing is that when you hit those nanostructures with a high enough frequency wave, they're energized in unique ways. And by energizing these atomic structures close to the surface of this surface, it creates, distortions, controllable distortions in the space-time field outside, right? And we're talking about the energy from that. It's a lot of energy, but the energy from that could come from a combination of fusion and some sort of 0 point energy coming from a space where you have another similar metamaterial, but in an opposite configuration, more or less, like polarities, but we're talking about like geometrically opposed configurational polarities. Wow. And that's set up in such a way, like an antenna for particles coming out of the void and whatever's coming out of the fusion reaction once you got that going. I was seeing a void for a long time, but you got me going the other night with the fusion. And I think that some aspect of both is appropriate. And Casimir waves are, I'm still coming to understand that, but how the what is this? The potential, that setting up that potential makes it so that the space-time waves change shape. The quantum waveforms inside and outside, inside this void versus outside the craft, change shape. And I used to boogie board, right? And I told you about living on a boat. So got to mute and pause. So I had a brief interruption, and you wanted to go into that. But yeah, go ahead.
So you hit on a few terms, a few key terms here. You hit on warping, metamaterials, superconductors, and Casimir effect. So you said you grew up on a boat, you used to boogie board. You're pretty familiar with boating. So let's start on the Casimir effect right now, just to start building base. So you know how like if you get two boats too close together,
yeah,
they start
falling toward each other. Yeah.
Do you know why that is?
I would think that there's not enough pressure between them, and there's sort of the dips connect in a sense. There's a what would you call it? A void.
So the waves between the ships are smaller than the waves on the outside of the ship.
Yeah.
And so the bigger waves exert more pressure. Right.
Is that kind of similar to how the reason an airplane wing lifts, or is that different?
That's different.
Okay.
So
so the waves are smaller inside.
Yeah. So when you get
outside of those two ships, but we're talking about space-time waves, but we're using the water
and you can
as a
use
metaphor.
Yeah, we're going to use water as a metaphor right now. So if you get the ships too close together, the waves on the outside will be able to get bigger than the waves on the inside. And so then the closer you get together, the more extreme that difference is, and the more they want to come together. Well, that's what's happening with the Casimir effect, only on very small scales with non-conducting plates.
Okay.
That also happens to be a really good analogy for gravity. So I'm gonna let you cook with that one.
Okay.
And we're gonna turn to warping. So you talked about like warping and folding a space-time, right?
Mm-hmm.
So come up with the warping up here. What does it mean when space-time is warping? Well, in order to understand this, we have to start understanding a little bit about general relativity. Now, general relativity was the theory that Einstein became more famous for, at least among physicists. When you hear physicists talking about the Einstein equation, they don't mean E equals mc squared. What they're talking about is this: G mu nu equals 8 pi G divided by C to the fourth, the whole thing times tisa mu nu. Now, what does this mean? I'm sure this is gibberish to most people, right? This is just a bunch of squiggly lines and things. So let's break this down. So what we have here this is called your scalar constant. Okay, so this is just a bunch of constants. 8 is always 8. It's a constant. Pi, it's a constant. This is G, so the Newtonian gravitational constant. Then down here, C being the speed of light, which is always a constant, and then to the fourth, 4, the constant. So this is our scalar constant. What this says, so this is your G sum mu nu. This is your space-time curvature, so to speak, right? And so what happens is, so you have your space-time curvature, and then you have your stress energy tensor. And so what happens is, as John Wheeler once said, space-time curvature tells matter and energy how to move, and matter
tells space how to curve.
matters. So you end up with this weird chicken and the egg
right.
So that starts to give you a little,
or both. Yeah.
So that starts to give you like a little intuition of what some of this stuff means. Now, where this starts to get more complex is these guys over here, these tensors, okay, is what they're called. So these are our second order tensors. So you have second order, meaning you have these two little notations right here, okay? So what does this mean? This is actually a grid. This is a way to compactify a series of a bunch of different equations that you have to do. So you're going to have your 0, 0, 0, 1, 0, 2, 0, 3, 1, 0, 2, 0, 3, 0, 1, 1, 0, 1, 2, 1, 3, 2, 1, 2, 2, 2, 3, 3, 1, 3, 2, 3, 3. And you do the same thing over here. And so what you're really doing is algebra for each one of these little equations on both sides. You start with the G00, and you say that your constants here act on it, and then that should tell you what the corresponding equation should turn out to be in this number one. And then you have to do that for each and every one of these. And it's really tedious.
Oh, sure seems like it.
And so what are these
equations
mapping out, right?
Right.
So you notice they're kind of in
are those vectors? Are those places you could end up?
Yeah. And so basically what this is saying is it's giving out your grid, and it's telling you where your geodesics or where your straight lines or how where the lines that like light and stuff will follow.
Right.
And then over here on this side of the equation where you're going to have brought out from that, this is going to tell you how much energy you should find in each one of these spots.
How much you should find. Is that for the use of the craft, or
no, this is just general relativity in general. We haven't even touched on the craft.
So we haven't even touched. Yeah. So I'm already connecting there. But that's okay. Okay, so that's how they determine, for example, how much energy is, in Jupiter, for example, the space-time energy tensor of Jupiter. Okay. Yeah.
So how can we relate? We're going to relate this to warp drive now. Okay. So in 1994, Dr. Miguel Alcubierre, he put out his paper, which I have linked here. It's actually not as important as people say. I'll get to it. Get to that why. But basically, all what he did is he says, because you can solve this equation either way. He says, okay, is there any shape of space-time that will allow arbitrarily fast travel, or a hyper-fast superluminal travel? And so he just kind of plays with the numbers, he plays with the shapes, and he finds one. And he's like, okay, we're gonna map it out, and then he figures out what the shape of it would look like as represented in this equation. And then he plugs it into this scalar, and it tells him how much energy he's going to need to make this, to make the warp drive. And what he finds out is that he needs 10 times the amount of energy in the universe, and he also needs 10 times the amount of negative energy in the universe. So it's
some huge impossible numbers there. And I understand it's gotten smaller and easier to approach. That's what I hear anyway. But you can probably explain that.
Yep. So when we have our warp drive here, we're gonna compactify this down to just a little two-dimensional plane. This is where space-time is. It's gonna have positive energy down here, and it's gonna get flat again. And then this is where a little spaceship is gonna ride. I'm just gonna draw a little rocket here then out on the other side, the warp rings around it just for continuity's sake, and now the drawing looks like shit because I'm not an artist.
Well, I was gonna make it. We're gonna work this up, and I'm gonna make a lot of really cool looking diagrams. Okay.
And so Let me make this thicker so people can see it. It's not that thicker. I'm doing a great job here.
That's my end of things, but this will have to do for now.
So this is where your positive energy is, and this is where your negative energy is. So it's making this bubble that
I see.
Nothing. So like if something was coming directly at the ship, like a photon, for example, it's coming directly at the ship. From the photon's perspective, as it goes around this weird line, it's going in a straight line. From the photon's perspective.
So it's just bending. It's bending around it, but as far as it knows, it's just went right through something. So that explains how at Skinwalker Ranch they could shoot these. It's okay. I'm going too far. You shoot a rocket right through it, and it barely seems like anything's there. So, anywho, the very cool. So, a question. So positive energy on this means a concavity specifically, and negative energy produces a convexity.
Basically, yeah. That's one way you can look at it.
Okay, or as like wells and swells.
Yeah, I mean, I'm sure you can find a 3D picture of like a 3D picture of what I'm trying to represent here. I'm sure if I Google it really quick, you just type in Alcubierre Drive and Google Images.
Right.
You're going to find something that looks like this, only kind of like laid out on a grid.
Right.
So I'm not even going to try to draw.
Now, in terms of other entities out there that we know of in the universe, physical entities like dark matter, dark energy, and I'm going to say, like, I'm going to guess, correct me if I'm wrong, but it seems like the positive would be more like dark matter and the negative would be more like our dark energy. Yes. Or
yep. That's a good analogy. Yep.
Correspondingly, okay, and or the positive energy is like black hole, the negative energy is white hole.
Yeah, and any piece of mass or positive energy is going to have a little bit of a positive effect like this.
Okay.
And so what's happening in, just if we wanted to relate this to black holes, so like on the event surface, on the event horizon of a black hole, you have these little negative or positive negative energy pairs that are getting split on it, and eventually one of them gets caught where it's close enough on the horizon where it gets sucked in. Well, the negative gets sucked in, and the positive gets sucked out, and then that's why the black hole shrinks, and that's that's Hawking entropy in a nutshell. We're going to get more into black hole entropy as the talk progresses. So don't.
We won't go too. Keep that in the back of my mind, right? I suppose a black hole would represent like as far as you could go down that road, right? And we're just talking about kind of more like dimples rather than outright straight punches through space time, yeah. Or
so, like, what do you mean by like a black hole is the limit?
Well, I mean, thus far, I don't really understand quantum gravity that well yet.
Well, nobody does. So we can get into that.
I've dabbled, and also it hasn't been proven yet. So, like, try to stick to general relativity as much as possible, even though I also don't really fully understand.
Well, we're not. That's the key point we're going to have to get into here.
Right, but the black hole, I'm still seeing somewhat as to a greater or lesser degree as in the old days. In ancient times, we saw them as a singularity that basically just went straight down and kind of, that the sheet doesn't really stop bending. It just kind of leads to somewhere else. Now we're more further evolved with Hawking and so forth, because he envisioned he's like, they're spinning, but how can they be spinning if they don't have a surface? And so presumably have a surface, and the spinning ones at least, and the larger ones at least have a surface, and those are encoding information. And so that's not obviously a singularity. And so I'm a little further along there, but relating to the original general relativity, like straight out of Einstein, hot off the presses.
This will probably be a really good time to segue into this. So let's keep the warp drive in the back of it.
Right.
We'll make one more quick thing.
And again, also this is the linear Alcubierre more like what you might see in the Enterprise. We're going further than this, and from imagining like the outward, inward, and
so there's been newer papers that improve upon this. Okay, where the energy requirements positively get dropped off a lot, so it's not as extreme. And we also learned from a multitude of papers, like from Heisenberg, Fell, Lenz, Boberg. Actually, Boberg doesn't talk about superluminal, but there's a few others that had, and then I can send you those out. Actually, I'll just send you a whole zip file that has like 30 fucking documents in it compressed. We figured out that we could still do this superluminal travel thing with positive energy on both sides.
Interesting.
And a lot less of it, just by playing with the equations. So all Alcubierre's paper did is introduce the possibility that, yes, the equations allow for it. And then that allowed more people to play with it more and more and more to get the energy requirements dropped down to a more manageable level. So we're going to get back into quantum gravity for a second, probably. Might be a good time to segue over here.
Okay. Yeah. Good. Prepare yourselves.
There's there's like caveats upon caveats upon caveats. It's
and it's based on string theory, and string theory hasn't been 100% proven according to a lot of experimentalists out there. So just a nod to the experimentalists. We see you, and we're continuing nonetheless.
I don't like string theory, and we're going to get into that.
I'm sorry. Did I touch a hot button? I'm not.
No, I was going to get into it either.
Now we're in the weeds.
There's a few traditional problems to this whole superluminal warp drive idea. We already touched on one, the negative energy issue. We touched on that a little. So once you say, okay, well, we have the negative energy parameters figured out, and we have brought down a bunch. The next argument, the most mainstream physicists who haven't actually looked at the papers, are going to say is, well, you still can't go faster than light because Stephen Hawking's chronological projection conjecture. Well, that's still just a conjecture. There's nothing in general relativity that disallows faster than light equations. That's specifically what these warp drive metrics are telling us.
It just took time for a guy to find the right equations.
Where it starts to happen is problems in causality when you go faster than light, because going faster than light is also going back in time. Is that a concept you're familiar with yet?
I've touched a little bit on it with Jack Sarfati videos. I'm still trying to understand. I know tachyons tunnel backward through time, but I also, as far as I've heard, haven't seen them. So
you hit on a perfect word, tachyon, right? So something that happens to these warp drives is as they accelerate beyond the speed of light, they start acting like tachyons. Okay. So we need is like a relativistic equation with tachyonic transition. So let's make a graph right here quick, right? So this is going to be our speed graph. So speed v for velocity. So v for velocity, and we'll put this point here as to set c for the speed of light. Okay. Mm-hmm. Now, what normally happens is it's a parabolic curve. The closer you get to the speed of light, the more energy it starts to take, because you start gaining relativistic mass, and then the more massive you are, the more energy it requires to go forward. So it starts. Mm-hmm. Mm-hmm. You start running into this barrier.
It goes up. Yeah,
it goes up to infinity.
Because the faster you're going, that's the same thing as gravity, basically.
Yep, and you're also going forward in time too, because of the time dilation. So you're also going faster and faster forward in time until you hit essentially what it might as well be the end of the universe. So, or the edge of the universal black hole, and we'll get into some of this terminology. But what happens if you have a tachyon that's going faster than the speed of light? What we find out, and I will send you papers that are you familiar with the Rand Corporation?
I've heard the name.
So the Rand Corporation, it was a think tank for the Pentagon and DARPA. basically, and then they do research for like the Air Force and stuff like that. And there's a Rand Corporation paper that studies tachyon physics, and it's like 60 pages. I have it linked.
Is that the teleportation paper, or is that something else?
Right here,
I've got okay. I have so many documents queued up from just the last like 4 or 5 days of being in UAP society. By the way, shout out George and Allie and Chris and Christy and everybody over there. Justin, you helped us get together for this, so appreciate it. Yeah.
This starts to mirror back on the other side. And so we have this curve that comes after, right? So this is basically coming from special relativity. And again, I'll send you some papers to go from this. And what special relativity tells us is essentially you have a budget of c, so you're always going the speed of light. Mm-hmm. Now, some of your speed is in time, and some of your speed is through space, and you have that velocity, or you have that budget that you can kind of trade. Mm-hmm. And that starts to sound a lot like Heisenberg's uncertainty principle, where you're kind of trading your uncertainty and momentum for your uncertainty and position. They're very close analogs to each other.
That's an interesting fractal connection there. That's
really, and we're gonna make a third fractal connection to that a little bit later.
Okay. It's black holes and micro black holes. I know.
Yeah, kind of with like wave function evolution.
Macro black holes, micro black holes. What's the difference, really? Yeah, potato, but go on.
So the faster that you go, faster than the speed of light, we run into this phenomenon where you start taking less energy to go faster. Okay. Well, we can glean a few things from this. One of them is that warp drives are going to have a top speed. Because there's always going to be a minimum amount of energy that you're going to need to keep your warp bubble going, right? To keep going faster than the speed of light, right?
Right.
Well, if I always have to have at least that much energy going at the same time, well, that means that there's going to be a limit somewhere as to how fast I can go. So the smaller a warp bubble is, the faster it'll be able to go.
Right.
So larger warp drives can go slower, or will only be able to go slower.
Go like that. Do you say
another interesting
go faster or larger? More energy means you can go faster, potentially toward the
more energy means you go slower for tachyons.
Backwards land. Okay.
Yeah, it's backwards land. It's weird.
Wow. That's like correspondingly, like it makes me think of imaginary numbers. In a weird way. In a backwards.
We can use this to our advantage to some degree with our warp drives, though. Because remember, in order to get to the speed of light, in order to accelerate to the speed of light, we had to go to the end of time. Because we traded all of our velocity for time, right?
So now we're at the edge of the universe, and our loved ones are dead, and nothing exists anymore. It's the heat death of the universe, basically.
Because we're also going faster than light, and we're inversing our time budget. Now we can go back in time.
So we slide down the other way.
Reverse it. Yeah.
Wow. Okay. So once you put all that energy, it's kind of like climbing a hill. Once you put that energy into climbing the hill, you can coast all the way back down. Yep. But the coasting is basically not just reversing gravity, but it is in a sense, but it's reversing.
Yeah, and then now there's some ways that we can get over.
It's interesting to think of time as a hill that we have to climb. And I caught what you did there with the inside of a black hole universe, because I'm hip to that. It could be that. We could be inside of a universe that's coded on a black hole.
I'm glad you made that connection. Mm-hmm. So that's good. We're going to build off that now, and we're going to start turning a little bit to quantum mechanics.
Okay.
And we're going to talk about a little bit about the history of the universe,
because it seems sometimes like these entities or UAPs are kind of in a weird way like outside that bubble and influence the goldfish. Or the cat looking at the goldfish, hopefully not a cat, more interesting humans that are doing their goldfish experiment in this metaphor. But the outside looking in and or Right. So members of another, not just another reality, but another reality that's encoded on a higher dimension, where this whole universe is basically contained within a bubble within. That's interesting to me, and I believe something like that. Like we're on a fractal, and there's lesser bubbles and bigger bubbles. And that's why I've never really liked the dark energy interpretation of the red shifting as like endlessly expanding, because it really gets in the way of this fractal perception. And I think a lot of it is perception. Yeah.
So I'm gonna give you a quick lesson and just regular quantum mechanics, so I can teach you why it's wrong. Okay.
Well, Einstein would love to hear that. That'll raise his ghost. That'll make his ghost a little happy.
It's a bit of a loaded statement. But I'll explain it. So I'm sure for any physicists that are watching this,
wrong to me, obviously context. Wrong to me means incomplete we all know that the pictures have not connected for almost 100 years now. And everybody's been fighting tooth and nail to try and connect them. And Einstein went to his grave trying, because they obviously bear out in experimentation. And we have hella data for relativity and quantum physics alike. And nothing we do would work if it were not the other case. And yet, here we go. So we're going to get into this. We're going to get into this.
So I'm going to take so let's just start with regular Copenhagen quantum mechanics.
Right.
So for any physicists out there, I want to start off. This is a somewhat of a dumbed down qualitative approach instead of a full on quantitative one. So yes, I know that it's a Straussian communication in the sense that for the physicists out there, you're smart enough to know that I'm getting some things wrong. We get it. I'm just trying to get some points across. So feel free to correct me in the comments.
Yeah, and no bad faith ad hominem attacks, please. We're just collegial around here. We want to discuss.
So we have a wave function, right? And it evolves by the Schrodinger equation. What do we mean by that? So we have our wave function psi, okay, and it equals something. So we're going to say it starts out by equals 1, or not 1. It's a bar. It's not a 1. Excuse me. All right, so we just start in this state, okay? We take this wave function and then we evolve it according to the Schrodinger equation. What does that mean? The Hamiltonian operator X. Now, essentially what the Hamiltonian operator is total energy. The total energy is the summation of the kinetic energy plus the potential energy. We're not going to get too far into that right now. So what happens when we act the wave function onto the Hamiltonian down here is we end up in an entanglement of two states. So at a wave, it starts to spread out, and this is where you get your weird superposition stuff. So we can start to say that psi equals half the square root of our initial state plus so it evolves and it goes both ways. We're in this weird superposition of states, and this is where people get Schrodinger, or some people get Schrodinger's analogy wrong. Originally, when Schrodinger first came up with this, he thought, well, this can't be right. This is why he made his cat analogy. He was trying to prove his own equation wrong.
Right.
You can't possibly believe that you have a cat in two positions. This is good so far. This is okay. Now, what happens in Copenhagen quantum mechanics is an outside observer comes in, and when he observes it, this initial state goes away, and we end up on one of them. What happened to the other branch of the wave function? Don't ask. Okay. And so we end up with this one state left over, where now we take that one that we found out again, and then we start all over. So now equals, and then we have a 1 here now instead of a 0 because this is our evolved state. And I have the 1s here now instead of 0s. And then we do it again. Well, where the issue happens is in this step with this is the problem where gravity has coming in. Gravity doesn't have a problem with it splitting. Gravity has a problem with just throwing one of the other universes away, and now we're just going to restart the system all over with this. And that's kind of what people mean when they say quantum mechanics is jittery, but general relativity is smooth. Well, so we're gonna play with this a little. What
my intuition is that the small scales to the big, and it's similar to, like, I don't know. I'm spitballing here because I do not like that's literally Greek to me. But,
yeah, literally Greek.
right. Yeah, it's something like the Buckminster-Fuller statement that the whole is greater than the sum of its parts, in that we have an emergent property of the observable universe that comes as a result of these minute quantum events that are somehow networking their way on up to where we see. And what the UFO, in a sense, does is modifies that through scaling those subatomic, what we would call quantum structures, in such a smooth way that it produces a counterintuitive result in our reality. Or am I going too far?
You're going a little far. So one of the things, so let's do a visual representation of that.
Keep pulling it back to the target audience.
So we have our started state, and we're just going to have a big circle here instead of our Greek equations, right? And then it evolves, and it could be one of these two states. Okay, now we got to pick which one of them. Okay, we observed this one. Okay, now we got to erase the whole thing. We start it over again, and then this one. Okay, and then it's that repicking process that gravity has a problem, because we know that the universe is accelerating. Well, what does that mean when the universe is accelerating? What they mean by that is when it's accelerating faster than the speed of light, it's actually shrinking. Okay, because our event horizon, think about it, the event horizon of our universe gets smaller because light can't get to us anymore because it's expanding faster than light.
I know about the horizon problem, but I'm still struggling to see that. So our horizon is
Big Bang smaller, okay. And then as time progresses, it gets smaller and smaller and smaller and smaller and smaller. And if we are looking at our universe from the inside out, we're going to be on one of these, watching it get smaller as time progresses.
See. So our visible universe is shrinking because space is expanding faster than the speed of light. Yes. I had not thought of that implication of that it was, in a sense, getting relatively smaller. That's new.
So now this is where we're going to say that quantum mechanics is wrong, but then right at the same time. Well, the Copenhagen interpretation of quantum mechanics isn't compatible with gravity. Everettian quantum mechanics is. Now, what do I mean by Everettian quantum mechanics? I mean the many worlds interpretation.
Okay.
The multiverse interpretation of quantum mechanics.
Yeah, Jack Sarfati was talking about this, how he's not into the Copenhagen any longer.
All Everettian quantum mechanics says is there's a wave function and it evolves according to the Schrodinger equation.
Okay.
So we start out with this state, and then it gets a little smaller. It splits into two, and then these two are entangled.
Dad?
And then
hold on. Let's go. Where were we at?
So we were talking about how the universe is getting smaller as it expands faster than the speed of light, right? And we were going to connect this as to why Copenhagen quantum mechanics is wrong and doesn't work with gravity, but why Everettian quantum mechanics, or the many worlds quantum mechanics, does work with gravity, but not in the same way. So when people mean they're trying to quantize gravity, they're trying to. So you start out with our states, and then you get the two entangled states. They're trying to make gravity fit into this mechanism, or you're erasing these other two, and then restarting with this other state, and then you're doing the whole thing again. Gravity doesn't fit in with that renormalization process. Okay. But when we have a wave function that just evolves according to the Schrodinger equation, and we just let it evolve without recollapsing it, and we let it decohere at or faster than the speed of light, and then there's some we can talk about some of Penrose's equation and how it relates to this a little bit later. And so I'm gonna go to a graph now to go with instead of our circles, but it's still representing our initial wave function state that I showed you with like what people mean when they're writing out when a wave function evolves and what the entangled states are. So got our graph x, y, and say this is like a space-time graph, and this represents the starting point of the universe, the Big Bang. Okay, well, we're going to just let it evolve according to the Schrodinger equation. It could evolve into one state, it could evolve into another. Okay. Just let it go all the way on down the line.
This seems like the
and you do
a
it
little bit
in every direction.
I'm noticing a fractal. This reminds me of the charts from the space-time tensor potentialities.
It should.
Indeed. Okay.
So
is that on purpose?
What do we notice? What do we notice here? We just let the wave function evolve according to our Schrodinger equation. Well, if we're inside one of these worlds, looking out at it as our light cones progress, holy shit, what does it look like? It looks like our universe getting smaller and smaller as it expands faster than the speed of light. So this is where the cosmic multiverse and the quantum multiverse are actually the same thing. Okay. Now this starts.
Yeah, no, I'm right there with the north. It's wow. Okay, I'm starting to see. This is interesting. Okay. Yeah,
and so these states are all entangled with each other, and this just happens. This happens naturally according to the Schrodinger equation, right? And the reason these are getting smaller is this is entropy. This is literally entanglement entropy. Okay. And so this really clever guy named Ted Jacobson, he did the math around behind this, and he figured out that you can relate the G side. Let's go back to our original Einstein equation that we started with. Our G-sa mu nu equals 8 pi G divided by C to the fourth equals T-sa mu nu. Okay, well, you figured out that and then we'll go back to our graph here.
Okay.
And then as these states are entangled, we can draw connections between them. And then we can measure the curves between these connections. Okay, well, this starts to give us a relationship to curvature, which is a measure of geometry on our Einstein side. Right. Okay, and entropy measures how much energy is in each one of these little curves. Holy shit, this is relating entropy, a measure of energy, to our stress energy tensor. It's when you just let the wave function evolve according to the Schrodinger equation, and you don't worry about a quantization mechanism, you find that gravity pops out through entropy. It's beautiful.
Wow. Okay.
So what we can really say here is we can start to reformulate this. We can say that general relativity is a semi-classical approximation of Everettian quantum mechanics. Okay, so we can start to say, okay, we're going to relate this to our tensor over here, and then let's just relate this back to what Pi says when he's talking about reforming Einstein's equations, where he's saying that the Planck force, C to the fourth divided by G, so C to the fourth divided by G, acting on space-time curvature, acting on our entanglement state, gives rise to matter and therefore density, our entropy. It's just reformulating Einstein's equation, but you're able to get it from a quantum mechanical perspective. So when we're going back, we should be able to solve this equation and get a quantum theory for warp drives, where our warp drive metrics in general relativity are a semi-classical approximation of quantum entanglement.
Okay. I need to do a lot more reading. Yes. First response. Second response, I need to one of the things I was planning on doing, by the by, is in addition to you, is plugging some of these papers in bit by bit to individual chat windows in GPT-4.
I've already been doing that.
And then bit by bit get it to process these, ask it pointed questions, and rather than just generically hitting up the bot for answers, program it, basically on individual rails to know what you're talking about and try to interpret the words of these individuals. So we're gonna have to take part 2 later in the night after the folks have gone to bed, and I think this has gone pretty good so far, and I think I want to process this a bit more. So I want to revisit. Can we revisit like later on? So that'd be 3 a.m. for you. So teacher, it's hours later. We were interrupted by reality, by a manifestation of Heisenberg's uncertainty principle. But it's now 3:40 a.m. and we're this is the dedication to getting the content out. I have an apple, teacher. I brought an apple and brought my notebook and I brought pens and pencils and and I'm ready to go.
All right. So can you see this kind of graph?
Yes.
Or series of graphs? Okay.
I can see it pretty well.
All right. So it's kind of recapping from earlier. We left off when we were talking about how we can reformulate Einstein's equation. Really bad handwriting. Holy shit. How we can reformulate through the work of like Ted Jacobson and Sean Carroll. How we can reformulate this and so find this and its predictions as a semi-classical approximation.
So is that AI G on top there?
Yes.
Okay.
Yep.
And on the bottom is, what's that symbol called?
C to the fourth.
C to the fourth. Gotcha.
Yep.
And that's the speed of light. Yeah, C.
Yep.
Same C. Okay. And after that is what? I can't.
T sub mu nu.
T sub mu nu. Yeah. For the sake of the. Okay. Mu is mu is a weird looking little thing. Huh?
Yeah, it's weird.
It's like a R with a extra length on the R. Okay. And
so just to recap really quick on what Bekenstein what Bekenstein has to do it, because that's the work it was formulated from, but we'll probably get to that. What they were saying was that if you can figure out the curvature of a black hole, so the surface area of your black hole, one of these will be, you can relate that as your proportion of geometry, and it'll be always proportional. So your entanglement geometry will always be proportional, or there's what can be measured as surface area, and will always be proportional to the entropy. So with that, so let's go to the one document that I sent you, titled Escape from a Black Hole with a Spherical Warp Drive, or something along those lines.
Gotta do some scrolling here. Let me bring this up. Yeah, you haven't been on Zoom before, so I might share this. Let me slow you.
And so this is a really important paper. I started screen share. Interesting.
Yeah, this is the one, right?
Yep. So can you go to the PDF?
Yeah.
Okay, perfect. So this is one of the keystone papers that we're going to build our theories off. So if you go down a bit, it's going to start talking a bit about the WD equals EPR projector. But this is the graph right here that we're going to focus on for the moment. Okay. So let's go down to this graph.
This one right here.
Yep.
Okay.
And so this is basically like a Penrose diagram. It's a space-time diagram. So to kind of explain to you what's going on over here, we're just going to focus on this upper right quadrant of this graph. Okay.
Okay.
And so now, if you look back at my screen over here,
okay.
See this 45-degree line that comes up through here? That is going to be your speed of light, which is constant, so it's always set at a 45-degree angle. This is coming out of basic special relativity. So normally everything that has mass will go slower than light, so it'll be on some vector. Where, because in the case of the space-time diagram, this would be your time dimension, and this would be your space dimension. And so when we talked about earlier, special relativity, trading your velocity in space and time, so everything that has mass has to go slower than the speed of light. So it'll always be in this section of the quadrant.
Now, would you include electrons in that, or?
So electrons have some mass, so they'll be in this realm. Yep.
Electrons, baryonic matter in general.
Yeah, anything that's going slower than the speed of light. Because remember, this 45-degree vector right here, this is our light vector. So anything that's going the speed of light is going to be going exactly at this 45 degrees. Okay, so electrons, they go really close to the speed of light. So just for an example, an electron might be following along this. You know, it's an approximation, but I hope you kind of get where I'm going for here.
No, conceptually, it's good.
Okay. So anyways, when we go back to our graph in the paper, what they're talking about is escaping from a warp drive escaping from a black hole with a warp drive. They're talking about going superluminal, or going about faster than the speed of light. So they're talking about going on a vector, and you'll look in the paper where they start here and they go to here. And you have an A, B, and C point. B right here is where you cross the event horizon, that kind of that speed of light part, right? And this will be represented in the upper right hand corner of that graph that's in the paper that I'm referencing.
Okay, I'm making notes and trying to annotate my diagram on my end too. So crossing event horizon. And where are you when you get to this other side?
I'm getting there.
We're getting there. Okay.
So this is where kind of the rest of the graph starts to come in.
I annoyed all my algebra teachers in the same way. I'm sorry.
No, you're fine. You're fine. So now let's kind of expand this concept out to a multiversal perspective instead of just one black hole. We can think of each little chunk of the multiverse that we experience as the parts of the universe we're experiencing. We can think of these as an individual branch of the wave function of the universal black hole.
Okay.
As there's a branch.
Yeah. Go over that one more time a little slowly.
So we can think of the universe kind of like a big black hole. We were talking about that earlier, right?
Mm-hmm.
And so because we're starting quantum first with an Everettian perspective instead of classical, black holes will have a wave function. Okay, and so we can represent this kind of whole graph as being the overall wave function of the black hole.
Okay, so black holes can represent a wave function. I need that. piece.
I can send you a paper by Sean Carroll called Branches of the Wave Hole. Yeah, branches of the black hole wave function need not contain firewalls. So let me look that up quick. Branches of the black hole wave function, no firewalls. All right, and there's the archive article right here.
So no firewalls is kind of like
no event horizons.
Right.
Pass through them.
Right. Kind of like where I was asking earlier about the delineation between Einsteinian black holes and where we got with Hawking and Susskind and apparently Carroll a little bit here.
Mm-hmm.
Okay. So there's no such thing in some ways as like a full singularity in this space-time. It's just
no, and this speaks to what Pius was saying too.
Okay. Pius. That's the name.
Pius. Yeah.
Pius. Oh, okay. I was a fan. I did
There
3 years of Spanish. It's Pius. Trust me.
Pius.
Yeah.
Fair enough. Okay. But where were we? Anyways, okay. So you're asking how this applies here. So in this kind of referencing off the Sean Carroll paper,
okay,
we can replace the word black hole with universe. So branches of the universe wave function need not contain firewalls, meaning you can traverse around it. So as we experience our normal flow through time, and so now we're going to write this as our time dimension up here.
Right.
For expanding out as our multiversal graph, so to speak. And remember, this is still like an approximation or a compactification.
Right.
So let's say our normal experience through time, we're always going forward through time. So up here, so this is going to be our point of maximum, the maximum point of entanglement, and this is our point of maximum entropy. Okay. So it gets back to the third fractal I was telling you about earlier when we were saying about when you can trade momentum or uncertainty and momentum for uncertainty in position, and the uncertainty principle is kind of analogous to how you can trade velocity through space and velocity through time, right? Okay. So what we're learning from this whole kind of multiversal Everettian perspective is that much like those two, how you can trade them, you can trade entanglement for entropy. So if you're in a state of high entropy, you have a very low level of entanglement. Conversely, if you're in a state of high entanglement, you have a very low entropy. Okay? And so through this lens, we can view the Big Bang as the universal point of maximum entanglement.
Right. So that's the universe at like Planck size, Planck temperature, the Planck sized universe, entangled. And that's what we kind of still are in a sense.
Yeah, that's one of the misconceptions about the Big Bang.
Right. It's still
the Big Bang wasn't.
Yeah. It's still happening, and or it didn't happen, and or is still happening. Yeah.
Mm-hmm,
the Vedas help me with this, like the Rig Vedas, very old stories about the structure of the universe. The egg, as it cracks, the cosmic egg as it cracks, and those fissures form, and those fissures are the webs of Maya, of illusion, if you will, of the separation of the egg, which is cracking and yet not cracked fully yet, right? So
yep. And so, how familiar are you with MC Escher's artwork?
Oh yeah, I love him. Right.
So look up MC Escher Circle 4.
Okay.
And that's like a take on hyperbolic geometry, and I want you to notice its similarities to when, if you look at that circle hyperbolic geometry thing, then go and look up observable universe and find one of those pictures where that kind of starts from the inside and looking out, and it kind of looks like a big eyeball. And notice how they're kind of painting the same picture in terms of their hyperbolicness.
Yeah, and it also reminds me in a kind of almost poetic way of what we talked about earlier about perception in and out of the looking glass, in and out of the kind of orb shaped mirror. The one he did, the woodcut of himself looking into the sphere with it's the reflection of his face looking back out, and so and you can see it's the reflection of his hand inversed and everything inversed, and that one always really tripped me out. Yeah. And I think that's powerful here too.
So think about that circle 4 and how it looks a lot like the observable universe is looking from the inside. Now, remember what I was saying about how this graph is kind of like it's a sliver. It's kind of a compactification. This branching happens in all directions. So we can extend this graph in a circle around here. Just kind of, and you can kind of sort of see here what I mean.
Right.
And when you think about it like that, it's the same fractal as that MC Escher circle 4, which looks a lot like the universe kind of looking from the inside out. Is the experiences that we're having.
Yeah, I'm seeing like the traversal of the macro to the micro, and or like, this sort of reminds, I mean, at this smallest scale, you've got all these really tiny interactions and all this information, seeming chaos happening, right? But it's just a matter of your perspective and where you're looking in a way. That's the Copenhagen collapse in a sense, where you're like observing, and now you're observing, right? Right. It's not really happening. It's your perception based on your placement on this.
Yeah, it just looks like it's happening.
Yeah. Oh man. Yeah, I can see this. And that's the connection between Einsteinian. Wow. Okay. Yeah, I've had this vision, for a while, but it's really cool to see it in the terms that other physicists can get. And I'm not just saying like, oh, hey, I've seen this before, but I had a sense of when we are doing warp, that what we're doing basically is condensing. It's condensation of information versus decondensation of information, or the perception,
creating entanglement for entropy.
Right. So are we saying that more condensed, when we're condensing information, and information, space-time, energy, tensor?
Okay. Let's keep building off this MC Escher circle 4 analogy.
All right. I'm running out of space on my paper. I think I need a new paper.
The whole thing about that is hyperbolic geometry. So no matter what way you rotate it, so like no matter what, so like if you were one of the angels or the demons on the inside of that, no matter what perspective of you're looking at it, geometry is going to be preserved.
Okay, I'm gonna have to pick this. Let's make this part of the thing. What's the name of this? Again, MC Escher.
Yes, there's MC Escher, Angels and Demons.
Angels and Demons. Okay.
Or like circle 4. Or
I'm just gonna screen share this really quick if I find it. Or I'm the one with 3 screens, so gotcha. Is this circle limit 4 woodcut?
Yeah.
Okay.
So now think if that was wrapped around a sphere, no matter what way you looked at it, the geometry would be the same.
Right.
And everything would be kind of the same size. So this is a really good analogy for what's going on here. So turning back to Einstein's general relativity, there's something called the equivalency principle. And again, this will be relatively familiar to most physicists here, is that whether you're moving through the universe or moving the universe around you, there is no difference, because you're always at the center of your own observable universe.
Right.
So the amount of energy that it takes for you to walk through the universe a certain amount at a certain speed is the exact same amount of energy as it is to just pull the entire universe around you at that same distance and speed.
Mhm.
It's you can think about it either way. They're both valid. So really, what's going on here with the warp drive, because we're always at the center of our universe, you're just entangling somewhere with wherever you want to rotate that sphere to look at.
Here we go. This is the image, guys. This one.
Yep.
Okay.
And you can already start to see the fractalness and how it starts big and then it gets smaller as it branches and goes out.
Yeah. Asher was a trip, man. He definitely got some stuff. Definitely. And the angels and the demons. Oh man, this reminds me. I think it was an Alan Watts quote. It's in a Ramses B song. Like when you're dying, quote unquote. Let's say no firewalls, right? It's kind of a coded message, and it's Bardot stuff too. But when you're dying, you're going to perceive that the angels, that either if you're not ready to let go, the demons are ripping you apart. But if you are, then the angels are taking you up to heaven. I mean, that seems like kind of a metaphor for black hole, and then just struck out at me here. But that was, I think, it was kind of a reference to the Bardot and the transit into dying, which is a really interesting. Like that's like our event horizon as a living being, and there's a lot of people that talk about the DMT state that you enter possibly as you die. The wondering if do we really die or do we just enter an infinitely
I guess that brings
perception
up
of time.
Well, thinking about Schrodinger's cat, what's the cat experience?
Right. Well, that's the question. Like of the Copenhagen would say, as soon as you observe the cat, you become aware of whether it did die or not. Right. And you can't look inside the box, but and it's some other people. Until then, it's in a quasi state of it could be either, right? But that didn't really ever make sense to me for photons, or at least it did.
It's always branching out, and they all happen. Quantum mechanics is like Murphy's laws. Whatever can happen does.
And I'm still not convinced on many worlds. I mean, like I'm pretty sure the branching happens, except it seems like that's just too much brain for the universe. I think there's some sort of error correcting code counter branching, but we're getting lost in the
so here's the argument for many worlds, and this is where it starts to relate back to warp drives, but I did send you a picture, by the way.
Okay.
And I want you to notice how similar that looks, and this is what I was saying about the observable universe.
Okay, I'm gonna pull that up too. Right. Saving all of these. I need a special folder for these things.
Well, so just to kind of keep going here while you're doing that.
Okay, yeah. Dead air.
Kind of building off what you were saying, how this relates to UAP in general. If the warp drive theory is right, and these things are going superluminal, they're going faster than light, means because what we talked about in that space-time graph about how when you go faster than light, you start going back in time. There's causality paradoxes in a single time. Okay, I'm sure you've heard about the grandfather paradox.
Yeah,
you go back in time and kill your grandfather.
That's why time travel, rubs some people the wrong way. I believe, but I've just not seen, the theory that gets me there. So please get me there.
So all those time travel causality paradoxes, they go away in many worlds. And one of the papers that I sent you, Time Travel Paradoxes and Multiple Histories,
I love
it goes
this picture,
specifically into this detail. It goes, and I can send you more papers on this too. But yeah, so you got the picture pulled up, so you can see the kind of the fractal similarities. Now, I hope.
Oh yeah, no, the billion and the I also, if we could really go on. the ratio between the Oort cloud to the center of the solar system, both in volume to volume, mass to mass, opposites again. You've got the electron cloud of the hydrogen atom to its nucleus. Not quite the cell. The cell's a little bit more even, but those extremes for sure. And then again, I imagine something like this when I picture a galaxy with all its dark matter, quote unquote, around it. And that it must be something like this. And then when I think about the galaxies themselves, you've got frog eggs, basically. I'm a biologist. If you were looking out of the nucleus of one frog egg, if you were a little tiny, minutia on the nucleus of a frog egg, and you were looking out, you'd be looking through a whole bunch of distortion, right? But in the sense of time, so like you were saying earlier, the light has to climb this hill, and it seems like maybe it's a little bit of a struggle to get out, and that's so it's in a weird way. Yeah, I've always imagined, well, a kind of that entanglement was maybe a part of this, and the resonation is a part of this, resonance is a part of this, and almost as if every location has a given space-time resonance. You could pop if you could get enough entangled energy state around your.
So a way we can think about this this picture here and how it kind of relates to our graph, we can think about the edge of the circle, because we can think of this as our semi-classical approximation of what one of these world lines will look like, right? So the edge of the circle where the Big Bang is, we can think about looking back in time to right here.
Right.
And then we'll be on one of these times looking back in time.
Whoa. Okay. And I don't know. Also, as again a biologist, I'm always looking at time in terms of an organism, and wondered if the way that organisms perceive time has to do with their size, right? And I asked my ecology teacher and my biology teacher this, of course, just a lot of annoying questions. But yeah, it's really interesting. Where the heck was I going with that? But that time also. There's a Madeleine L'Engle book. I don't know if you read those books. Wrinkle in Time, A Swiftly Tilting Planet. They're books about tesseracts, wormholes, aliens. I'm surprised you haven't read those. The second one, they kite. It's this method of mental astral travel, and they go into the mitochondria of inside. Like her brother's having a sickness, or he's being invaded by these beings of darkness that are invading his cells in the same way they're like this is cascading effect on the planet, and that darkness is affecting people. But they kite in to the cell, and time is totally different. They're like, is that the heartbeat? They hear this sound? Like, heck no, that's thousands of years. We hear those once every thousands of years or so. And there's what you're hearing is this some, subtle rhythm of like the ATP synthase and the mitochondrion going off and stuff like that. But the time perception was different. Has hit me hard for years and years. But this is
sort of a relative concept. Have you
exactly. It's based on the perception of entropy. Entropy and other things going forth. And I know, I've heard that the arrow of time is kind of a structure that we created. And Men in Black, the galaxy, that galaxy's eye is on Orion Belt. Or go ahead.
So let's go back to this graph here, right? That we were kind of.
I will stop sharing. Sorry.
Oh, yeah, no worries.
I'm having a little bit of a mini DMT experience, given the time and the nature of the subject matter.
Take all the downloads.
Yeah, all at once.
So in that warp drive paper where they were talking about escaping the black hole, they just started here on your line, and then they did a straight line acceleration,
right,
to get on the other side of the black hole. Now, what that would look like in this graph over here is going like that.
Okay. So really, yeah.
So there's a slight problem with this, though. Okay, you can't instantaneously accelerate. You can accelerate very, very, very rapidly. That might seem instantaneous from our perspective, hence, UAPs, but there is a gradient of acceleration. It's parabolic. Right. But so what would that look like on this graph? It would start to look like a wave, because we start going slower than light, and then we accelerate faster than light until we cross that line. And then we can keep going faster than light somewhere. And then when we slow down, we got to start going back slower than light again. And then this will speak to, remember that graph I was showing you earlier about how the relativistic barrier goes up and then back down for tachyons. So there's you go forward in time and then you go backward in time.
Yeah.
That's that same concept represented on a different type of graph here with a wave.
Okay.
Instead. Okay, so now let's expand this out to the whole graph instead of just this one little subsection of the graph. What this would really look like, so let's say we start on this timeline right here. We start somewhere in this universe. We're going to start accelerating slower than light because we're already going this way as time progresses anyways. And then we're going to go faster than light and go back in time. But say if our destination's over here, well, we got to ride this wave until it intercepts. So we can calculate we can calculate what the wave is with trigonometry, and then we can figure out how much energy will be expended in this wave, and then we can use that to calculate back on our Einstein equation to figure out what shape of warp bubble we need to follow along this trajectory. And then we can calculate a wave that'll intersect along any one of these arbitrary points anywhere in the multiverse. Given if you have enough amount of fuel and stuff. But.
So when we're observing, in some cases, like when these things quote unquote like blip out, sort of flip out, they do this.
Yeah, when they're like
they warp. There's a warp, and they like change the shape, and then they go. And they disappear, right? So that's them kind of going between these, not between worlds or out of this world per se, but they're drifting, they're intersecting these points between space-time perception windows.
Remember,
and then when they're coming in, that's that they're appearing the exact same way in opposite fashion.
Yep.
Okay. So in some cases we may not even be involved. This is beings that are traversing multiple dimensional kind of black hole miniature perception universe bubbles that are
now remember, our conscious perception, and I can send you papers about this, already traverses this, but we experience it going forward time like all the time. So we just kind of go through one of these trajectories. Where free will starts to come in for us, though, even though the whole thing evolves deterministically, we can make decisions along the way to go, all right, well, I want to go here. Well, maybe I want to do that. So we can kind of zigzag forward in time. And then if we figure out how to build a warp drive, we can go, oh, okay, well, here, I'm going to go check this out.
Oh, gosh. So you could see not only the past per se, but also potential realities that could have existed or could have branched out. Hypotheticals. Interesting.
Yeah, and then so you could figure out,
plus that all the exos and other planets that are becoming their own versions and all this other stuff as well. So as I tell my kids, like, you can't think of anything in this universe that doesn't exist, because chances are space-time has thought about it in some form or fashion. My kid had a really weird dream last night, and it was far out. And I asked him to describe the characters. They were not human, and the plot line was not human. And they're speaking English. I'm like, I suppose that's possible. But
somewhere, yeah.
It's got to be some combination. Lobsters with feathers, and it's turtles all the way down.
So one of the problems with that some people have with many worlds is they're like, well, is this an infinite amount of worlds or is it a finite? Because some people want finite, some people want infinite. So, well, the answer is there's a hard and soft version that answers both.
I believe so as well. I think so, that letting it take it to the infinite again, the Boltzmann brain of the universe would just explode. You'd overload. What did we talk about earlier? You'd overload the data capacity of the black hole, the software hair that's holding our universe or coding our universe, wouldn't you?
I disagree. I think you just wake up on a couch with a bong, and then his friend would be next to him. How is the human?
Was it a trip, man?
Sitting there holding the bong with your tentacles, like what the?
Although that does interesting, and the dream metaphor reality thing, Matrix, MC Escher holding the ball of the guy looking out at the guy holding the ball. It reminds me of a story connected to the abduction phenomenon. This guy studies. Wow. Okay, so get in the esoteric a little bit. This guy studies owls and abduction experiences. Which owls are a big part of my life. I don't want to get into owls, but he said after years of studying this, he realized that he was not only having these experiences himself and had buried it, even though ironically he's an abductee. He had an experience that led him to understand and recall that he, in a way, was a gray. And I think this is kind of a weird coded metaphor. Like I studied the Wanjinas, I studied mythology, obviously, not just ancient Eastern or Western mythologies, but the indigenous stuff. What I'm getting to is he had the revelation. He was one, and he was in here experiencing this 3D reality, and he kept saying, "It's so difficult. It's so difficult." And they kept saying, "You volunteered for this. You volunteered for this." Was the answer that kept coming back from these grays on the other side of this meeting room, conference room, which is obviously ridiculous. It was a coded metaphor of some kind, a Jungian archetype, but it was these grays in Nazi suits, in tweed suits, in a smoky room, right? And these
rocking the Hugo Boss outfits.
Yeah. And again, it could be anything. Don't leave anything out just because it seems far out, right? And I'm like, that sounds like some sort of altered Earth where we really screwed up at the end of World War II, and the atmosphere caught on fire, and all we had was a little bit of human tissue and some basic cloning technology. We just made do, right? Somewhere along the line, but the metaphor for the experience of being here in this third dimension, experiencing, or in this experience, experiencing something that's part of, and the Midnight Gospel is a lot like what you just said too.
Yeah, Midnight Gospel. Of
course, yeah. Right. Wow, man, that's a really intense session. Okay. Right, and I obviously need to dig more into the nuts and bolts of the.
So we can apply a finite number to the multiverse, if people are uncomfortable with it, and basically how we do that is, and this kind of gets back into black hole entropy, and then Jacobson and Carroll's work on specifically this, and I can reference you to some of their lectures because they'll be able to explain this in depth more than I will. But in essence, the dimensions of Hilbert, so the dim of Hilbert space being the wave function is just a vector in Hilbert space.
Hilbert space is new to me. I saw you bring it up in chat. I didn't want to admit I don't
So
know what that
Hilbert
is.
space is just the so dimensions in Hilbert space are different than dimensions and like space time dimensions.
Okay.
All those dimensions are is in Hilbert space is the number of degrees of freedom for a quantum system.
Okay.
I'm sorry, I can't give you a much better explanation than that.
No. This is important because the dimensions we know of what space, time, and what beyond that, space, time, energy, the amount of energy packed in space and time. Those have always seemed like that's what we can see, right? But at some level, either the insanely micro quantum or the insanely macro universe level, those don't really mean anything, and they're replaced by other dimensions that have more validity in that context, right? So similar to how dimension could also, like, we have a dimension called temperature, and that is actually a measurement of how much energy is packed in a certain amount of space and time.
Yeah, so that's one of the weird things in physics right now is like depending on like which branch of science or physics you're exploring in, dimensions have different definitions.
Yeah,
which gets confusing for laymen.
Right. So you have the four dimensions, maybe slightly more from Einstein, but then string theory has so many different dimensions. And then
remember, string theory is a quantization of gravity. What we talked about earlier about them starting with the wave function, then seeing how it evolves, and then they come up with a quantization mechanism to get rid of them, and then they start over the whole thing again. And that it's one of those weird ad hoc ways that you can make that work, but it's.
Yeah, it reminds me of going about science in a way that you're doing constants, right? I've always hated constants. Like, constants to me means you don't understand the theory, because that means your numbers are coming from your experiments, and even in this case, if it's mathematical thought experiments, you're kind of testing. It's guessing and checking, right? It's not the formula itself. Am I far off?
So we can say that the dimensions here in Hilbert space, right? For at least in our quantum context, if we want to, technically it's infinite, but we want to apply a finite number, so we're going to apply a Planck scale cutoff. So this is what people mean when they say a UV cutoff. So on the bottom here, we're going to put our Planck area, so Planck length squared. Okay.
Dimension.
So then for
Hilbert
the
space.
upper size, so we just take whatever the upper part, so whatever the overall the boundary size of our system is. So we can say we could do this for any arbitrary system, and we find out we take the mass of what that system is. We find out what a black hole of that size would be, and then we measure the surface area of that black hole in Planck areas.
Okay.
And then that gives us the dimension of the Hilbert space for that system. So if we're talking about a black hole the size of our observable universe,
right?
Okay, so which we can call the Hubble volume. Okay, what that comes out to is roughly 10 to 120 branches for our observable universe. Now, the number could be bigger because we don't know how big the universe is outside of our observable universe.
But, so Hilbert space dimensions are the dimension of Hilbert space is measured in branches.
And that's sort of kind of.
Okay.
Again, I'll refer you to other lectures and papers that can explain this better than I will, because there's more qualified people than me to do it.
Right. Then something like Jupiter would be obviously much smaller than that.
Yeah, and we can play with this too. We can say, like, okay, well, what's the mass of me? Okay, and then we figure out what the size of a black hole, the mass of me would be, and then we count that in Planck areas, and then we figure out, okay,
you're just dropping this mass in the numerator here. Just any old mass in newtons, or what? I'm just wondering how the unit maybe somebody else could help me figure this out, but like, I'm assuming
there'll be other people that can explain this.
Yeah, units cancel out, right?
Interesting. Very yeah, and so this has to do and I'm going to tie this now into what David Grush was saying.
Okay.
About the holographic principle. He got it slightly wrong. This isn't the holographic principle. That's ADS-CFT corresponds, but this is holography.
He's not that kind of a physicist, is my understanding. He was like trying to just poke at the edge of the elephant.
Yep.
Very badly.
It's not ADS-CFT correspondence. It's slightly different, but this is holography because the information, the dimensionality, the overall entropy of our black hole, which is equal to the dimensions of outer space, is defined by its surface area and not its volume.
Okay, hold on a second. I just had a thought I'm gonna write down for later. Experience data. Okay. Like getting a download. Oh, okay. Now you're going to have to say that last little piece. So this isn't holography, or this is a kind of holography, but it's not necessarily the same as the holographic principle that Hugh is poking at. Okay, it's a kind of holographic, but it's a kind of holographic coding on and at like the edge of one of these perception bubbles, which reminds me of like, well, everybody wonders what thoughts are, right?
Yep. And so when he was saying, oh well, it has to do with the holographic principle and other dimensions, what he's calling other dimensions is these other branches of the wave function. So the other branches of the multiverse.
Okay. Other branches. Now that's always confused me too, because we have Sliders dimensions, and these sound a little bit more like Sliders dimensions to me. Did you? Is that too old? Too far back for it?
A way that I like.
Sliders was a show where they hop between dimensions, like physical places where they would go, and that's obviously different than either. Right, it's a term that needs definition based on where you're talking, your crowd that you're addressing.
Draw you a little graph here, just to kind of give you like an idea of sort of where I'm coming from.
Okay.
So we're going to draw our X, Y, Z dimensions. We'll just do a really simple two-step graph. Do.
This also seems to pertain to where the information is coded at the edge of the cell, like in the electromagnetic bioelectric field of the cell. Somehow, the perception barrier itself and how that scales up in terms of the consciousness of the individual or the intelligence of the individual cell, its purpose, its membrane of self, its what do you call it? Markov blanket. Right. That's Carl Friston, which is all these guys are dancing around in my mind, but where the energy information potential of the life cell, planet, galaxy, black hole is coded at the edge of this one of these squares and or Hilbert spaces. Okay, and that whoa, yeah, that was the thought. But go on by all means.
So a way I try to like to think about this. So think of each one of the, and this is going to sound sort of like string theory, but it's the opposite of string. In string theory, they're little tiny. The extra dimensions are little tiny loops that kind of wrap up around each other. This
right.
Isn't that. But we do want to think about each one of the X dimension and then the Z dimension or the Y, the X, the Z, our T and our M, and then however many more dimensions we might need to make this work. We can think about them all as a big.
Wait a second. What's M here? My bad.
Our multiversal dimension.
Multiversal
That's just what I'm calling it. Just
and
to give
we've
it away.
inversed the chart. Okay, noticed.
Yeah, sorry, I inversed the chart.
It's all good. I was in La La Land having a DMT download straight to my brain at 4:28.
And actually, I'll probably just show you the one that I already have. So each one of these dimensions can be thought of as so it's kind of like our Earth the horizon looks flat, but we know Earth is actually round. If you zoom out enough, eventually it wraps back around on itself. So eventually, each one of these dimensions in a finite multiverse will wrap back around onto itself. Mm-hmm. Okay. And then if we come up, we're going to come up to the one that I already have built up here. You can see kind of how we can think of they each kind of knot form into a knot around each other. And so then as they get more and more entangled towards the Big Bang, the knots are closer together. And then as they get more and more entropy, the knots get farther apart. Oh shit, it's about to die. Let me plug it in.
Yeah. Okay, you're gonna have to go
now
rabbit hole again with me really quick. I'm sorry.
So can I finish this thought quick?
Yeah.
So shit.
I'm getting pinged too.
So all of these they kind of wrap around and knot together with each other. Okay. And then the different interactions that they have, the manifolds when they pass through each other, these are Lie groups, and then this starts getting into like fiber structures and geometric unity, and Eric Weinstein can describe all this stuff better than I can.
Right.
But the interactions between these dimensions will define like the different laws of physics and the different particles and stuff. And like if you can probably pull up like a picture of E8 lattice. But anyways, to get back to your original question, where the branching happens. So you start out and then it branches, and then it branches again. So but what is this? This is remember, this is representative of a wave function. So you start out with a big wave, and then the wave spreads out into a slightly smaller wave, and then it gets a little bit more diffuse through each one. And then each one of these different waves represents different ways that this wave could have propagated as it's interacted with, or as these kind of dimensions have interacted with each other near the point of as they kind of traverse and rotate from as they trade entanglement and entropy.
Okay.
So that's where the branching comes from.
Okay. So it's a finite branching, and their interactions sort of almost entangle each other as they branch and rebranch, and in a way these
so there's only a finite amount of ways that they can interact with each other. It's a very large amount, but it's still finite.
And these potential avenues for interaction are jumping here, but these are the routes that you can take. Originally the GD6 that you could take between through.
Yep. So these are our levels of entanglement. How these knots are tangled together, and relating this back to Einstein's equation, entanglement we can relate to our space-time geodesic, the GISA part of the equation. So yeah, you're on the right path.
Okay. Can you do the other part of the equation just really quick for our guests? Again. And that's
so then building off
that's
building
8 by
off
8. Or see the fourth T. So mu. Okay. I'm writing mu as a tiny mu. I don't care if I make people angry.
People are gonna people are going to complain no matter what. I can't wait to see
I'm obviously going to add a tiny Mew Pokemon just for a second and post right here. Yeah.
So
wow. Okay.
This is our entanglement. So the geodesic of how the curve of how these dimensions are acting together gives rise. It tells us what their entropy is going to be. Okay. And so now,
how far along? In other words, it's on that time-like curve of the universe unfolding in that particular Hilbert space trajectory on one of these universal light cones.
If we can figure out the amount of entanglement between us and our target branch, okay, well that gives us a measure of entanglement that we can now convert that to Einstein's equation, and then that should give us what our warp field needs to be for that location, and then now we can figure out how much energy through just through the basic Einstein equation, we can figure out how much energy we're going to need for that specific warp event. So now we're starting to come full circle back again.
Right. So and then then my brain wants to jump to navigation, and what am I thinking? The epiphany came to me some years ago before freaking Discovery morphogenetically stole my idea for Spore Drive. I was thinking of the way you might get information and discover entangled. Well, there might be some way to jump through entanglement through these potentialities as the universe unfolds. And how would you do that? Where would you find your way? And it occurred to me that DNA is a kind of encoded entanglement it's a record of all the interactions it's had all the way along the line.
So,
okay, and then so you could possibly use that, or maybe what kind of information is holographically encoded in like the electromagnetic sphere of the Earth.
What is entanglement? It is the Einstein-Podolsky-Rosen paradox, the EPR. Okay. Now, can you pull up that escape from a black hole with a spherical warp drive again?
I'm also wondering about do you know how they achieved entanglement between particles on purpose and like the energies involved there? So like we're basically in that experimental context, like stacking up to those energies, right?
So you're talking about like how do we get the energy for the warp drive?
No, I'm if we're talking about entanglement, I'm confusing. I don't want to confuse terms here. So we've got Einsteinian entanglement, and how is that related to, like, for example, the discovery of that we can entangle particles?
Einstein, Podolsky, and Rosen, they came up with the concept of entanglement. That's right. Why it's called the EPR paradox.
Right, but since then,
as they called it.
Okay, we've found since then that we can entangle particles on purpose, and
yes, that was what the Nobel Prize last year won for. Yep.
So how do those? How does
the ER?
How does the concept relate to the experiment?
So you're starting to talk about the ER equals EPR experiment, right. and if you pull up that paper, this is exactly what I was going to start.
Okay. Okay.
Yeah. So no, we're going on. We're going down the right path.
On the right page.
So
okay.
What the ER equals EPR paper says. So ER equals Einstein-Rosen bridge.
Positive energy. I've got escape from a black hole, spherical warp drive, positive energy.
Yeah, escape from a black hole.
Is that the one we're looking for right now? Back to it?
Yep.
Okay. I'm sorry.
So this wasn't the Nobel Prize paper, but we're going to relate it to the Nobel Prize paper in just a second.
Maybe get that PDF back up again. Okay. It's on right where we left it. Okay. And I've got to go to bed soon, and we've got to pick up again.
Okay, and this will probably be a good last note to leave it on.
Okay.
So again, Einstein, Podolsky, and Rosen came up with EPR paradox, entanglement. The spooky action at a distance. They also came up with the Einstein-Rosen bridge, which is a wormhole. Okay. What in 2013, what Leonard Susskind and Juan Maldacena proposed is the ER equals EPR conjecture. Is that these entangled particles are connected through tiny wormholes. Okay, and then that was experimentally confirmed through, and they basically made they entangled like a series of like six particles or something on a quantum computer. You'll have to look up the what the Nobel Prize for it was, like inequality, confirming inequalities in Bell's theorem or something like that is what they called it. Again, I'm sure people will flame me for not getting the title.
That's much more interesting than just kind of the buzzy headline that I read. I didn't read the paper, obviously.
Yeah, so now ER equals EPR is saying that these entangled particles are connected through tiny wormholes, and that's speaking again back to the connection that we made through entanglement on the geodesic here. Anyway, so let's scroll down in this paper.
Okay.
All right, got the plane wave. Let's keep going. I mean, I'm sure nerds that are going to understand this math want to see it.
Yeah,
but
not me
I'm not
yet.
going to go into these.
I'm not there yet. I would love to work this out. I would love to finish the proof. I love
Keep going.
I love this stuff, but like it was really, really good. And this none of it actually seems that much more complicated than stuff I already learned in school. But this is my problem with traditional education.
All right, so they're here.
They teach you the math, but not the application. I would have much rather they just gave me this.
Page 6. Okay. So this section 5 and 6. So the micro warp drives and evaporation of singularity. They give us an equation right. Okay. And then this can start to tell us what the energy of our warp drive will be. Okay. So what it's saying is the energy of our warp bubble is equal to the velocity of it times the radius squared divided by the thickness, whole thing times the c squared divided by big G. Okay, and then this is going to tell us how much energy our warp bubble is going to need. Now, if you go down and you start to read about it, and if we assume a Planck scale and a Planck radius,
I'm getting a close up of this. I'm got to take notes, and that's the way I'm going to remember it.
So, if we assume that these are that we're going to put the speed of light over here to c, and we're going to do the Planck scale or Planck ratios. All right, these start to cancel out. Okay, this combines, and what do we end up with? What do we end up left over with?
I'm going to go back to you really quick. Yeah.
It's LC to the fourth divided by big G, which is relating exactly where at the end of the Einstein equation. So what this is telling us, and if you'd gone back to the paper and read the conclusion, we can assume now from this that not only the ER equals EPR conjecture, we can now say that warp drive or WD equals EPR. Okay.
Okay.
It talks about ER equals EPR down here. Yep. And so what this tells us is essentially warp drives are just a type of wormhole, which are approximations of entanglement. And then you can use it to traverse around you can use it to escape a black hole and traverse the universal wave function, i.e. the multiverse.
Right.
And then next time we can start to get into how exactly we modify the space-time geodesic to make these warp drives, and we can get into that next time. Now that we have this baseline established,
to make it, and not just that, it seems a little scary. Honestly, like you're going to end up in. For example, I have a model Millennium Falcon that fell apart and stuff like that, but I put it in a fish tank back here. And I like to joke it's what happened to Han and Chewie when they went through the wrong wormhole one time, right? You don't know what world you're going to end up on, what size.
Hyperspace calculations ain't like crop dusting, kid.
My goodness. He talked about bouncing a little bit too close or go through a star and whatever in his context, but shoot, you're going to end up in some kid's fish tank being eaten by an alien planarian.
And so it gets even more complex than that too, because we have to make sure that we're not back. No, we're not. Well, because our warp drive, as it goes faster than light, is going to emit Cherenkov radiation. Okay, so we have to make sure that we're not getting too close to anybody's planet nearby, so we're not X-raying people as we pass through their branches. Right. So really, ideally, you want to come out of FTL velocities and transition to slower than light at a safe distance from your target, and then finish the journey at slower than light speeds, which that kind of speaks to, in sci-fi when they're like coming out of hyperspace or warp speed and stuff like that.
You don't want to do it inside the atmosphere, as they say. Interesting. I have to shout out Bruce Colville, the writer of the Aliens Ate My Homework and my Teachers and Aliens series from the 1990s. Okay, Aliens Ate My Homework. The character, the way the aliens did it was using wormholes to jump between dimensions, and the difference in size and the perception of those dimensions, somehow they were able to weave between multiple scalar dimensions of different sizes in order to basically weave their way through space to their destination. And it was that he had it. It sounds like some more or less
analogous, yeah.
Yeah, and that was a weird book. I mean, it's kid stuff, but I got to go get those again for mine. But interesting. Yeah, that's all been baking my noodle, and just to see this, I appreciate your time explaining this to me and helping me along this journey. And it's so much weirder than just UFOs. It's really that's the ontological shock.
It's not. They could be from another planet in this timeline, but given the implications of multiversal travel, they could be from any planet in any timeline,
any when, any where, any size,
including
any shape.
And this is the scariest option. They could be from an alternative timeline on our Earth.
Right. Which
what if it's one where the Nazis won?
Well, one where the Nazis won, or like I said,
it's out there somewhere.
Alter Earth, where let's say a world where that very tiny chance that as they said, when the nuclear bombs, they were testing the first nuclear bomb, that the atmosphere would light on fire. Right. Some incalculably small chance, or calculably very small chance, but that chance happened, and that universe exists somewhere where the whole sky got scorched in a blazing instant. And that those creatures, what would evolve on that planet? Trisolarans and every other kind of nasty thing. So but again, would they be able to construct warp technology to get here? And so it's kind of like a Fermi paradox thing, but warp, in the sense that you can get out of a universe or get out of your Hilbert space if you can construct technologies that arrange space-time and information in such a way. Okay.
And so I honestly think Star Trek is a good analogy for this, in the sense that the Federation doesn't reach out to you until you build a warp drive,
Right. Right.
And so I think there's some kind of prime directive at play here where they can watch, but to build off Eric Weinstein's analogy, if the uncontacted tribes in Andaman Island start building airplanes and we're seeing mushroom clouds on it, and they figure out how to build a jet plane and start flying around. Well,
it's only a matter of time.
Yeah, we might want to go talk to them.
Well, yeah, give him TV for a few decades. That's another Bruce Colville trope that he dropped in there. How do you take care of the fact that the humans are advancing so quickly? Just give them program television. Watch what happens.
Yeah, but then they figured out the internet.
Yeah, no, exactly. Everything's advanced. It changed so much since YouTube came out. now they're trying to stop that. And there is actually a piece of history there in the sense that the DoD did debate whether or not they were going to release the internet. In a sense, like it was a real question. Like, do we do this? And then there, you got the novelty, Terrence McKenna's novelty wave. Once you do that, all hell breaks loose. So then there's the other risk of like, what if you, so if you, the prime directive thing, you accidentally crash land on one of these worlds and the monkeys or slugs or whatever the heck they happen to be crawl up on your ship and graft their tendrils into your warp drive and get out, right? And they're not supposed to have that stuff. That, I mean, Animorphs, I don't know if you
I mean, if it was me, I'd be like, all right, let's watch. We'll keep our finger on the kill button, but let's see what he does.
Right. Just as soon as they're crossing outside their bubble, like, well,
the question is, does he do it safely?
Yeah. Are they going to be good? Because I guess in all universes, jacking warp drive is a potentiality. And I suppose that's what some military industrial elements of our own sphere are trying to do, but my belief is they're too compartmentalized. They don't think like this. They're not, let's be super open. Let's throw all the
unless they already have it, but
or that too. I mean, there's both arguments that they already have something, that they have something like it. Maybe they can't get off world per se because somebody's watching, right? And you have this viral kind of anti-spiritual, call it anti-philosophical tendency, and you don't take care of your population very well.
What I'm really curious what's going to happen, because it's going to happen at some point. It's just a matter of when. At some point on one of the timelines, we're going to build one from scratch of our own design, and we're going to pull up next to them because they won't be able to outrun us anymore. And we're going to be like, hey, what's up?
What's up? Yeah. And then you're kind of on an equal footing. But I mean, you were talking about scales here. And then there's Kardashev out there with the different.
I don't like Kardashev.
Yeah. This sort of violates that. It's sort of like short circuits it, just like one of those little hilberspace short circuits, in a way. And I've never been a total fan, but if you take that model and imagine what he would call a K2, K3 civilization, or well, I guess the scale thing doesn't really work out then, does it? Like, you can't really base on scale because you've got all these scales.
I don't think the Cardashev scale works.
Dimensionality goes whop. Like a Bose-Einstein condensate when all of the particles are turning into waves. Basically. Maybe that's a segue to next time we talk about the metamaterials, the superconductors, and this kind of.
Well, and I don't believe when people say, oh, they have to be millions of years more advanced than us. Well, obviously not. They're still crashing, allegedly. And we can figure out the same physics. So we're not that far behind. It's an engineering project at this point. It's no longer a physics project.
Right.
I mean, the closest thing to a physics question now is a navigation equation, so we don't get lost.
Yeah, exactly. You don't want to. There's a million potentialities.
We might have to take baby steps with that too. We're like, oh, we're going to test this out. Let's do a 1 light year and see how far we're off.
Yeah, we happen to crash land in this atom on the collar of like Stephen Hawking 30 years ago, and we can't tell anybody about it because it's actually this really weird space colony in a whole other universe.
Well, I think people are really going to shit if we find other life out there, and where it's like, oh, it's us.
Yeah, happens probably a lot.
And then they're just like, oh shit, yeah, we left your planet 15,000 years ago. You don't remember?
That's that, and that's just one linear dynamic. But you could have several branching patterns that go out in full circle.
Mm-hmm.
Now, Gary Nolan investigated like the Atacama humanoid, and they found out that it's not that different from human. It's just got a few chromosomal abnormalities that happen to line up on these very, very specific and nuanced.
It was a deformed fetus.
It was a deformed fetus. Okay, now hear me out. Was a deformed fetus, but if you say had humans leave the planet and go off on a trajectory, and just as an example, it may well have been that, but as an example, they go out and they go through one of these bubbles full circle, they go warping, they go a full universe, almost of time, and they're still technically human, but they've got all these changes that happen to adapt them to life in space, life in zero G.
Are they close enough genetically to form viable offspring? There's your answer.
Yeah, and a whole population of those, and eventually that population would phenotypically and genotypically be expressed in something like.
I've thought about that a lot. Is like how many different like races or ethnicities or phenotypes the human expression has throughout the multiverse.
Are we looking at
fascinating?
Are we looking at some part of our future that ended up somewhere in our past, and yet somehow also affects our present and somehow also our future?
I would say that might be a possibility, but given the multiverse implications, causality is a bit more slippery than
right. Is there a potential of landing in your own universe, or are you always landing in some other universe that looks a lot like yours?
Just to make another graph. Sorry, I'm not getting.
That's what the causality question comes to me. Like, can you really trigger the grandfather paradox, or if any time that you're landing in something that seems identical, it's just one atom off and therefore not.
So I would say when you accelerate forward and then you go back in time, you can end here. I'm not going to say you can go straight back in time, but you might be able to kind of jump around like that and then kind of skirt either next to it or, skirt around your life where you wouldn't remember it, because there might be some ways, but I don't think you can directly go back in time.
Right. Okay. That makes a little more sense
to jump around.
Okay. You jump around. So the Marty McFly, obviously, example, which that movie's made for normies, and it's a terrible representation of how time might actually work, even from a standard linear thing. It's full of paradoxes that are above and beyond the standard paradoxes. But if Marty went back, when he goes back to the future, and then other Marty that was grown in a different future goes back and goes back and goes back. There's a loop there of like endlessly dying Martys, but it's not necessarily the case that he even has to go. Every time he's going back, he's going to a slightly different universe version.
Yeah, I would say the Everettian quantum mechanics is Murphy's laws in the sense it's not everything happens, it's everything that can happen does happen. Does that make sense?
Yeah. So not literally everything happens, but everything. Okay. And there's those subtle branching differences between those.
Yeah. There's nuance.
One is finite and calculable. The other one is infinite and incalculable. Wow. Well, my friend, it's 5 o'clock in the morning here.
All right.
I've got to go to bed.
All right.
I'm going to take a nap tomorrow, though. Everybody, don't worry about me. Daniel, you've made my week, year, decade, and I appreciate the time you put into this. And we're only going to go further down this,
and we'll keep building on this and letting it snowball as we do more.
Okay. And on top of it all, I got my own official homework to do. That's hilarious, and it dovetails. It dovetails. Um, um, Got to hit the end button in this sesh.
All right.
Love you, man.
It's good seeing you, man. Thank you.
Yeah. Thank you. Bye.